In the next lecture, we are going to look at some specific examples of how one can use the limit definition of the definite integral in order to compute the integral of some actual functions. So the first example is to compute the integral from a to b of x dx. Right, so this would be, so if we graph it, we have x. So there's f of x is equal to x. And we want to compute the integral from a to b. So it literally would be the area of this trapezoid. Now, we know what the area of this trapezoid is, so we can, for example, represent it like this. We can divide it into a rectangle and a triangle. So the area of the rectangle is just going to be the height here, which is a, times the width, which is b minus a. So this is b minus a times a. Now, the height up here is b, so this vertical distance is b minus a. So the area of the triangle is going to be 1/2 b minus a squared. So if we add the two together, we would get 1/2 b minus a squared plus a times b minus a. So that gives me plus ab minus a squared. If we expand this out, we get 1/2 b squared minus 2ab plus a squared, and then plus ab minus a squared. So this isn't using any of the technology we have developed. This is just seeing what the area of this trapezoid is. So here we have minus ab, because the 1/2 times the 2 is 1. So we have minus ab plus ab, so that cancels with this. So we have 1/2 b squared plus 1/2 a squared minus a squared. So 1/2 a squared minus a squared is minus 1/2 a squared. So the whole area is equal to 1/2 b squared minus a squared. So that's the value we should get for the integral. So let's see, maybe it's not so complicated. So let's look at the integral from a to b of x dx. Well, first of all, we need to set up our Riemann sum. So delta x is going to be b minus a over n. So this is for a specific n. So we're going to assume that b and a are given. So they're basically parameters that, they're essentially going to be given. So we're going to treat them as constants that are known. X sub I is a plus I delta x. Right? That's just the general formula for the Riemann sum for x sub I. And then we'll use a right-hand Riemann sum. So f of x sub I will just equal x sub I. So f of x sub I is just equal to a plus I delta x. So this will be actually our height for our rectangle. And then the delta x will be the width. So basically, f of x sub I times delta x is going to be a plus I delta x is b minus a over n. And then it's all times delta x, which is b minus a over n. If we expand this out, we get a times b minus a over n, and then plus I b minus a squared over n squared. So this will be the approximate value. So this is the area of the ith rectangle. So what we have done, if we look at the picture, here's A, here's B. We've divided into pieces, and we're doing a right-hand Riemann sum, so we're taking the height of the function here. We're looking at this rectangle. The height of the function right here, looking at that rectangle. The height of the function here, looking at this one. The height here, like that, and then finally the height here, like this. So this is the area of our ith rectangle. It's literally just x of I times delta x. And then we use the definition of delta x and x sub I to write it in terms of I and n so that everything is clear. So the Riemann sum, so our right-hand Riemann sum with n subintervals is going to be the sum I equals 1 to n of a b minus a over n plus I times b minus a squared over n squared. Now, this is a constant, and this is a constant relative to the sum. So it's the sum I goes from 1 to n, so we're treating everything else as though it's fixed and just changing I. We have the term I is equal to 1, I is equal to 2, and so forth. So the first term is just a constant term, which is summed together n times. So if I sum a constant together n times, I get n times that constant. So this is going to be n times this constant is just going to be a times b minus a. And then plus b minus a squared over n squared times the sum I equals 1 to n of I. Now we know what this sum is equal to. When I sum I from 1 to n, I just get n plus 1 over 2. So here's a nice simple formula for the right-hand Riemann sum with n subintervals. It's a times the quantity b minus a plus b minus a squared times n plus 1 over 2n squared. And in fact, this n can cancel out with one of the n's down here, so I can get rid of the n squared, and I can get rid of that n. Just like that. So I have a nice formula that I actually don't have to go back and compute my Riemann sum over and over again because I have a nice formula. I did everything just in terms of the formulas, and I ended up with a formula that you tell me what n is, and I'll tell you what the Riemann sum is for this integral. So I'll tell you the Riemann approximation for the area under the graph y is equal to x between a and b. Now the only thing we have to do next clear some of the space, although these are wonderful equations. I hate to see them go. It's so nice, those equations. So what we can do next, let's go back into pen mode, is the integral from a to b of x dx is literally just the limit as n goes to infinity of my right-hand Riemann sum with n subintervals. So that means it's the limit as n goes to infinity of a b minus a plus b minus a squared n plus 1 over 2n. Okay, well we know the value of this limit. This first term is constant, so its limit is just going to be a times b minus a. And as n goes to infinity, we have n plus 1 over n. That's the relevant portion here. So n plus 1 over n, the rest of it's just a constant because now we're taking the limit as n goes to infinity, so we treat the rest of this as a constant. N plus 1 over n just approaches the number 1. So the second term approaches plus b minus a squared over 2. And this looks very familiar. This is the one we expanded out earlier. So that just gives us b squared minus a squared over 2. So thus we have just shown that the integral from a to b of x dx is equal to b squared minus a squared over 2.